Hiya, this is Mr. Baker, and today we're going to be looking at electrical power and potential difference. So today we're going to be looking at electrical power and potential difference. You'll be able to look at the electrical power of a device and what kind of things might affect it, calculate the power of systems, and then also you're going to be able to explain why different things might have different types of power. So first of all, have a look at this. This is a little bit of a recap of some of the things we've done before, describing how household electrical appliances can be made safe.
How is household wiring kept safe? The majority of the electricity we consume comes via the mains. This electrical energy is generated in power stations and uses alternating current, or AC, which flows backwards and forwards around a circuit. This means that you can't strictly talk about one terminal being positive and one terminal being negative as you would with a battery, because they're changing all the time. Instead, one wire is said to be neutral and is literally connected to the earth at your local substation, so it's relatively safe. The other is called the live line, and its potential, or voltage, becomes positive and negative relative to the neutral line 50 times a second. This is why we talk about mains supplies delivering alternating current at a frequency of 50 Hz. Slightly confusingly, the peak potential difference of the mains supply is actually about 320 volts. But because the voltage is alternating, most of the time it's below this peak value, meaning that when you connect it to a resistor or a light bulb, these behave as if they're actually attached to a 230 volt battery. So to make things a bit easier, we normally talk about the mains being 230 volts. 230 volts can easily drive a current through your heart that's large enough to kill you if you complete the circuit by touching the live line. Also, if a fault develops, like a short circuit, which provides a low resistance connection between the live and neutral lines or the ground, it can produce enough heat to start a fire. Owing to these dangers, electricity suppliers go to great efforts to make systems safe. Mains conducting devices like plugs, cables and light switches are surrounded by insulating plastic. This prevents any dangerous leaking of currents. To provide extra protection, electrical devices are also earthed. An extra cable, which is traditionally a yellow and green colour, is connected to the neutral line at the substation and via plugs and cables to the cases of any connected electrical devices. This means that if a live wire accidentally touches the case inside a device, the current will drain harmlessly to earth. Without this safeguard, the case could become live, meaning that if you touched it, you would be electrocuted. Another way that mains circuits are kept safe is the use of devices called fuses. These consist of a thin wire with a low melting point. If a sufficiently large current flows, it will heat up, causing the wire to melt and blow the fuse, interrupting the circuit and cutting off the supply. And because the fuse is designed to melt at a much lower temperature than the wire used elsewhere in the wiring system, this safety measure can help to prevent large currents from causing wiring to catch fire. A fuse should be connected to the live side of the circuit so that when it blows, any connected appliances become safe. In a plug, the brown live wire should therefore be attached to the fuse. The blue neutral wire should be connected to the other short pin, and the striped green and yellow earth wire is connected to the longer topmost pin. There are different ratings or sizes of fuse which will blow at different currents. A device should have a fuse rated slightly higher than the maximum current the device will draw when it's working normally. This means that the fuse will blow if a fault draws even just a small amount of extra current. But using too large a fuse could mean that it will never blow, despite a dangerous fault developing. However, the current at which a fuse blows is still likely to be about 1,000 times higher than the current needed to kill someone. So although they make devices safer, fuses are generally unhelpful in preventing a person from being electrocuted. Instead, this is the job of trip switches and circuit breakers, which can detect even very tiny short circuits and interrupt the flow of electricity before a person is harmed.
A fuse is basically a piece of wire with a very low melting point. And if there's a fault in the electrical appliance and the current goes up, it could damage the wiring in the appliance. So a fuse is installed and that will melt and break the circuit instead. So have a look at this example here. So here we've got an ammeter, and you can see that the ammeter is low, and you can just about see the wire inside the fuse there. As the current goes up, can you see this needle going up here? As the current goes up on the ammeter, you can see the fuse starts to glow red hot. It's getting hot as the current goes up, and then when it gets hot enough, it melts. Okay, and so on the ammeter now you can see that there's no current flowing because the circuit is broken, and so this can help to stop a electric circuit from becoming damaged because the electric current goes up by too much. So we use different types of fuses. Domestic appliances are fitted with a fuse that suits it. So we normally use fuses that are 3 amps, 5 amps or 13 amps. And that means that if more than 3 amps flows through a 3 amp fuse, then that will be too much current for it. It will melt and break the circuit, and so no more current, will be able to flow through. Right, so how's that linked into what we're doing today? So it's all to do with power, really. You've looked at power before. The definition of power is that it's how much energy is transferred over a certain amount of time. It's the rate of energy transfer, or the rate that work is done. Okay, so this is the general equation that you've seen before. But when we're talking about electrical power, then we have a slightly different equation here. So the power supplied equals the current times the potential difference. Okay, so electrical power is the charge flow per second multiplied by the energy transfer per unit charge. Okay, so it's still in watts, it's still talking about the joules per second. So we're still talking about an amount of energy transferred in a certain amount of time. But when we've got an electric current flowing, we multiply that by the potential difference in volts, and we can work out the power. We can also see how much energy per second is dissipated to the surroundings by something. So this equation here, we look at the current squared times by the resistance, and that will also give us power. So it's just another equation that we need to sometimes use when working out the energy that's transferred every second when electric current goes through an electrical conductor or a resistor. Okay, so we've looked at a few things to do with electrical power and potential difference. So you'll need to go away and you'll need to practice using some of those equations. Think about why and how fuses work. And we've done all of these things here. We've stated what the electrical power device is. You've seen how we can calculate power. And then we've also seen how we can calculate the electrical heating using the power equation too. So that's it for this one. I'm Mr. Baker. Stay well. Thank